Today, these tourists are enjoying a beautiful climb on Sydney Harbour Arch Bridge. However, around 90 years back, there was a big challenging day for the workers of Sydney Harbour Arch Bridge. The joining of two half arches. They braved a heavily windy day and riveted the arches together on the same day. Otherwise, they may not have had another chance for this. They constructed such a rugged arch bridge that it can even handle the weight of trains. Did you notice the beautiful curve in this bridge? The interesting thing is that if they had designed the bridge with a circular shape, the result would have been a catastrophic failure. Obviously, a long road deck cannot stand like this without support. This is why this kind of gigantic support structure is used in arch bridges. The road deck is supported by this support structure via hangars. But what ensures that the support structure will stand strong without collapsing? We need a strong, self-supporting structure. Remember, the support structure is supported only at the ends, not along its length. Such a move would obstruct the movement of the ships below. Here's a thought-provoking question. Out of these shapes, which one is the best self-supporting structure? Very soon, we will find out the answer for this logically with the help of an interesting King Kong example. Now, let's find out the answer using a simple experiment. When we apply a weight to this circular wood block arrangement, it just collapses. However, if you place weight on a parabolic shape, it stands strong. In short, the parabolic arch is the best self-supporting structure. Now it's the engineer's duty to convert this parabola to a practical structure. Welcome to the construction innovations of the Sydney Harbour Arch Bridge. The construction progressed from both ends as half arches until they were connected in the middle. Let's observe the construction phase more closely. Can you find something wrong here? If the bridge is constructed this way, the arch will fall down because of the gravitational pull. Please note the arch is supported only at the bottom points. To overcome this issue, many support cables were drilled into rock at the end of the half arch. A fleet of creep and floating cranes were used to execute this construction feat. Individual arch members were brought from a workshop on a pontoon boat. They were later lifted up and assembled using creep cranes. The arch members were first joined using bolts. After adjusting the final angle and position, rivets were used to secure the entire structure. About 6 million rivets hold the bridge together. The weight of this arch is around 38,000 tons. Even after all the structures were erected, the arches had a gap of 3 feet between them. Now comes the trick. Just release the support cables of the arches one by one. Their own weight causes the arches to slowly move down and eventually touch each other. Hooray! It's celebration time! They riveted these two pieces immediately after they touched each other. This impressive arch spans 1,654 feet and stands 440 feet from water level. Now it's time to prove logically why the parabolic shape is the best self-supporting structure. Let's tie a gigantic chain across the mountains of the New River Gorge. Thank you, King Kong, for your help. The shape this chain forms is a parabola. In fact, the true shape of a freely hanging chain is a catenary. Even if you try to hold it in some other shape, it won't stay there. A chain can support only a normal tension force. Now the tricky part. Let's solidify this parabolic chain. Now, let's flip the direction of the gravitational force. Since the external force has flipped its direction, the internal stress will also flip its direction and become purely compressive. Now, just flip this entire arrangement. Wow! It becomes an exact arch bridge. The compressive force developed by this parabolic structure is exactly at the middle of the section. Such structures are always stable. You can see why a structure may not be stable when the forces do not have this quality. This is why the parabolic arch is the best self-supporting structure. Now let's construct a road deck below this arch. However, there is one more way to achieve the same objective. Just shift the supporting arch down. Here, again, the force induced in the arch is the same. If you were the chief engineer in charge of this project, which design would you choose? Obviously the above deck design, right? The reason is simple. You will save a ton on construction materials. Does this mean that the engineers must always choose the above deck design? Let's try this design in the Sydney Harbour Bridge location. As you can see, we quickly run into an issue. There's an insufficient amount of space between the road deck and the river for the arch. Shall we try an underwater arch design? No. Such a design would block the ship movement of a huge area. That's why in this location, the only design possible was the road deck below design. Here's an interesting question for you. Do you think it's possible to construct a road deck that is completely below the arch? There is an issue with that. The arch must be connected with the ground. How can we modify this design to achieve that? The only way to connect the arch to the ground is by extending a portion of the arch below the road deck. This is precisely what engineers did with the Sydney Harbour Bridge. Such bridges are called through-arch bridges. The most suitable type of arch bridge to be constructed depends entirely on the geography of the location. Did you notice these enormous bearing hinges at the bottom of the bridge? Interestingly, during temperature change, these hinges allow the arch to change angle, as shown. If there's a temperature increase, the length of the arch must also increase. Thanks to those bearings, the bridge can adjust its angle to accommodate this length change easily. This way, the engineers ingeniously avoided the issue of thermal stress in the bridge. You'll be amazed to know that the Sydney Bridge rises by almost 7 inches during summertime. Along with this arch expansion, the hangars also expand due to the temperature changes. This ensures that the position of the road deck is not affected. In this illustration, you can clearly see how this enormous hinge is fitted with the ground, as well as the details of the foundation. We already know how they constructed the arch. One clever construction trick they played here is that they constructed one side of the arch faster than the other. The idea was that if there was a mistake in design or construction of the arch, they could rectify it on the other side. Now it's time to connect the hangars. One end of these hangars have a V shape, and this portion was first fitted to the arch structure. Now let's see the details of how the steel workers attached the cross girders of the deck to the other end of the hangars. For balancing purposes, they started the assembly of the road deck from the center and gradually worked their way toward the ends. You can see that the road deck structure does not actually touch the main arch structure. This clearance ensures that the road deck is unaffected when the arch changes shape with temperature fluctuations. The total width of this 12-lane deck is a whopping 160 feet. The road deck has 4 railway tracks, 6 lanes for road traffic, and 2 lanes for pedestrians. The cool thing is that the pedestrian lanes are positioned outside the arch. Upon completion of the bridge, 96 locomotives were positioned in different ways on 4 lines to test it. In 1958, 2 of the railway tracks were converted into roadways. Now a question arises. Why didn't they opt for the suspension bridge at Sydney Harbour, even though it's more economical and easier to construct? Suspension bridges always sway. When the bridge has a heavy load to handle, like a freight train, you must opt for an arch bridge design. The arch bridges are more rugged. The under-construction Chenab Bridge in India is one of the best examples of it. It's also the world's tallest rail bridge. The load acting on the bridge structure, in this case the weight of the train, has a big impact on the internal stress developed and stability of the bridge. The previous analysis we did only considered the self-weight of the bridge. We already saw how the internal stresses flow perfectly along the body center when the shape is parabolic. However, when there is an external load on the arch, the internal forces deviate from the center line, even though the arch shape is a parabola. If we connect the positions of these internal forces, we can make something called a line of thrust. For good stability of the arch bridges, the engineers make sure that even under extreme load conditions, the line of thrust remains in the middle third of the arch section. An interesting arch bridge type we didn't discuss in this video is the tied arch bridge. To learn about it, please check out our exclusive video. Thank you for watching.